Okay, last question. Pigpen for 10 points. Consider an electron-positron pair, E minus and E plus. It's known as positronium, and they have a love-hate relationship. Because they're oppositely charged, they have an attractive potential. They love each other. Unfortunately, they're antiparticles, and so they destroy each other in very, very short order. And there's a couple different spin states which have slightly different lifetimes. The question is, what are the energy levels of this system in Rydberg for hydrogen, and why? Okay, this is sort of the typical freak you out question. There's always going to be one on these exams where we're being pushed to think about, apply the principles of the unit and of quantum chemistry to a slightly unusual problem. And so here's the way the 10 points break down. It's not too hard to get some of them here. So the first part is to realize what the potential is. It's always how you set up a problem in quantum mechanics. Figure out the potential. So here we have a single negative and a single positive charge interacting with each other. So step one is to realize that the interaction potential is exactly like the H atom. So the potential is 1 over 4 pi epsilon naught times minus 1 over the distance between these two things, R1, 2. It's a hydrogen-like system. The energy levels are going to be hydrogen-like for the system. And so that's basically 3 points in the grading scheme. A little less than a third is just to say this is a hydrogen-like system. There's a positive and a negative charge here. It's going to look like hydrogen, one way or the other. So the next part is, well, okay, now that I know it's hydrogen-like, what are the actual energy levels? And in hydrogen, the regular hydrogen, this has something to do with the nuclear charge. There's no nucleus here, but we do have a +1 and a -1 charge here. So the second part is to say, well, what's different? The difference has got to be that in the hydrogen system we depend on the reduced mass, and here the reduced mass is half the mass of an electron because we have two identical mass pairs. Normally the reduced mass is basically the mass of an electron because the electron is 2,000 times lighter than the proton. So basically the reduced mass for hydrogen atom is just an electron mass. Here the reduced mass is a half of that. So this has got to affect the energy levels. And it's really the only thing that's going to significantly affect the energy levels. So realizing that is the next 3 points in the answer. Now, which way? Well, in general, if I have a lighter system, the energy goes up. So the energy levels, think way back to the particle in the box. The smaller the mass, the higher the energy. And so in general, we expect the energy levels to be higher, meaning the system is going to be less stable. Now mathematically that might come out a little different here because our zero is the dissociated system, and the energy levels are essentially going down. But we expect the math to work out so that that having a lighter object is going to send the energy level up. It's going to be less stable. So that's the next 2 points, and that's most of the question. So the last part, the last 2 points, are what the energy levels are like. And you may have written this down in the first place. The energy levels for a hydrogen-like system are actually minus reduced mass times e to the 4th times divided by 4 pi epsilon naught all squared, and also divided by 2h bar squared times 1 over n squared for n equal 1, 2, 3, etc. So there is the hydrogen-like energy levels. They go like 1 over n squared, and we've pulled out what we normally write as Rydberg constant for hydrogen, and you see that the reduced mass is in the numerator here, but it's a numerator of an expression that has a minus sign in it. So there's the reduced mass, and the energy levels actually go like minus 1/2 a Rydberg times 1 over n squared. So by cutting the reduced mass in half, we make the energy levels go to a half a Rydberg as the characteristic value. And so you notice that the mass actually shows up in the numerator, but because of the minus sign, this means we're going down less far. So the energy level is negative a half a Rydberg, as opposed to the hydrogen answer of minus 1 Rydberg for hydrogen. And then again 1 over n squared for n equals 0, n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to infinity. And so So doing this weird thing, getting rid of the nucleus, making the positron-electron pair, in the end, what we've done is we've changed the reduced mass, and by cutting it in half, the energy levels, it gets less stable and proportional to mass by a factor of 2, and everything works out. So that's good. And there was also some other information there that you didn't need. They are factually correct. Their lifetimes, they're different for singlet and triplet states, etc., etc., etc. But this is the information you need. That's another aspect of some of these kind of more challenging problems, is that sometimes there'll be information around that you don't really need to answer the question.